All right, hi everybody. Today we're going to continue notes that we started yesterday. Make sure you're filling out your note packet. If you need an extra one, they're in the light blue crate by the door. So make sure you grab one of those, get it filled out. I will be checking them on Thursday to see if you actually did it. And after you go through the notes with me, then you can work on whatever you need to work on. If you cannot seem to stay busy and not mess with other people, there is an extra starry night for you, but everybody else will have no homework tonight other than an Odigia quiz. That'll be due next Tuesday. So just make sure you stay busy, find something to do when you're done, and you'll be just fine. Okay, so yesterday we ended with characteristics of waves. We talked about a crest and a trough. The crest is the top of the wave, a trough is the bottom of the wave. A wavelength is between two crests or two troughs. Then we talked about frequency, which is the number of cycles per second. So basically, how many of those wavelengths can we get through in a second? And then speed is the distance that wave can cover in a specific period of time, whether it's kilograms per second, meters per second, just whatever, depends on what you're measuring with. So let's talk about wavelength and frequency. So visible light, that's the light that we are actually able to see with the naked eye. And they all the colors have different wavelengths to them. Red has the longest wavelength, while violet has the shortest. And then once you get towards orange, yellow, green, blue, those wavelengths tend to change depending on what color you're dealing with. So anytime you look at color, so for example, if you look at my whiteboard and you look at the green wall behind it, what's happening is the color green is being reflected into your eye at that wavelength, so you're then able to see the color green. Also, same thing with any other color that you deal with. It reflects off whatever object you have. Everything else is absorbed, so you don't see it, and that color is then reflected into your eye. That allows you to see that color. And depending on the wavelength, it's going to tell you what color it is. So wavelength is measured in meters, and frequency is measured in seconds. So it's related to that equation right there. Again, we're not going to solve for anything. It's just good to know. And C always equals the speed of light, which is 300,000 kilometers per second. So as the wavelength gets shorter, the frequency gets higher, and vice versa. So the closer to violet, ultraviolet, X-ray, gamma rays, all that wavelength is getting shorter, meaning there is a higher frequency of that ray getting through. Vice versa, towards red, infrared, microwaves, radio waves, those rays tend to get a lot longer and more spread out. So that would be, it has a lower frequency because they have a longer wavelength. Okay, so let's talk about light. So light is a photon. So a photon is a packet of energy. So we call light traveling as a particle a photon. There is argument whether it is a wave or a packet of light. We say it behaves as both. So here's a little bit of history of light dealing with waves and photons.
Man has always wanted to extend his activities past sunset. Fire was his first artificial light, but it was difficult to transport. Then came grease lamps, gouged out of soft rock. These allowed the first artist to go deep within caves. Each new form of light marked an era. The grease lamp that must be regularly refilled, the candle that drips on one's fingers, the kerosene lamp, smelly and dangerous, until, around 1900, the arrival of magical electricity, as bright as daylight. Light has long been considered divine. If we go by our cultural references, the Greeks were the first to study it. For them, light was closely linked to vision. The mathematician Euclid had the brilliant idea to represent it by thin rectilinear threads, luminous rays. He believed that the eye sent out rays to strike objects, which allowed them to be seen. Civilizations disappear, but libraries remain. In their conquest, the Arabs recovered Greek works and translated them. They inherited ancient knowledge, deepened it, and brought further innovations to it. In the year 1000, Alhazen understood how the eye functions and confirmed, contradicting Euclid, that light comes from objects. Even more importantly, based on countless experiments, he put forth the laws of reflection and refraction. Alhazen symbolized Arabic science at its apogee in the Middle Ages, a new science based on observation, experimentation, and measurement. His books were translated into Latin and circulated throughout Europe. Copernicus, Kepler, and Galileo read them and were inspired by them. As with many other areas, it was a renaissance for science. Galileo passed from geometric optics to instrumental optics by creating a telescope that he pointed toward the sky. He discovered thousands of stars in the Milky Way, craters in the moon, Jupiter's satellites, here is Io, and sunspots. He asked himself, how fast does light travel? He wanted to measure its travel time between two hills in Tuscany using flying lanterns, but in vain. These instruments were too primitive. The experiment would have appeared pointless to René Descartes, who believed, like most scientists had since antiquity, that light spreads instantly. In 1637, he established the law of refraction, but also searched for a solution to the problems of geometric optics. He had the great insight to return to the nature of light and launch a debate that would last 3 centuries. 25 years after the death of Descartes, the Danish astronomer Ole Romer, working in Paris, studied the movement of Jupiter's satellites used as clocks by navigators. He perceived irregularities. Io, for example, rises later and later as the Earth gets farther away from Jupiter. Romer attributed this gap to the additional time taken by light to reach Earth. He estimated the time at 22 minutes for light to pass through the Earth's orbit. He could calculate the speed of light using simple division, but unfortunately, orbital dimensions were still not well understood at the time. However, the result was there. Light has speed, and this speed is not infinite. This was good news to Huygens, the Dutch mathematician and astronomer. It supported his theory that light is a wave, a vibration that travels. His theory conflicted with that of an eminent English thinker, Isaac Newton, for whom light was a stream of particles. Each of the men interpreted the phenomenon of light in his own way. Take refraction, the changing of direction of light when it passes from one transparent medium to another, from air to water, for example. For Huygens, if there is refraction, it is because the speed of the light waves decreases when they penetrates the surface of the water. Newton, on the contrary, used the rules applicable to the ballistics of projectiles. If there is refraction, it is because the speed of the particles increases. This wave-particle controversy would inspire generations of thinkers after them. In the early 19th century, Young, Malus, Fresnel, and Arago discovered the phenomena of diffraction, interference, and polarization, which proved the wavy nature of light. But Newton, who had found an explanation for the gravitation and movement of planets, had received immense glory, and many thinkers called Newtonians remained partisans of the particle theory. To define his theory, Arago proposed experimentally comparing the speed of light in water and in air. Foucault and Fizeau developed revolutionary laboratory equipment to determine the speed of light, the first using a rotating mirror and the second a serrated wheel. The key experiment was conducted in 1850. Verdict: the speed of light is slower in water. Huygens was right. The triumph was completed in 1865 when Maxwell achieved the brilliant synthesis of electricity and magnetism. Light is the sum of two waves, an electric wave and a magnetic wave. Light is an electromagnetic wave. Was the debate definitively closed? No, for in 1885 Hertz showed a new phenomenon. A metal plaque lighted by ultraviolet light emits electricity, while with red light nothing happens, even when the intensity is increased. This photoelectric effect is impossible to understand if light is only a wave that carries energy. Inspired by Planck, Einstein gave the credit back to Newton's particles. He announced in 1905 that light is composed of quanta, later called photons, particles without mass whose energy depends on the frequency of the associated wave. Thus, depending on the nature of its interaction with matter, light manifests itself as either a wave or as particles. It would take some time to admit this subtle truth, this wave-particle duality, which was stated by Broglie in 1924. Light is a truly exceptional phenomenon in the history of science.
All right, so that showed that for the longest time we believed that it was a wave and that's all it was, even though Newton was saying, no, it has to be this particle called a photon. Well, we then find out it actually behaves as both. It's a group of photons traveling in a wave that help move the light particle through. Okay, so inverse square law for light. So as light radiates away from its source, it spreads out in such a way that the energy per unit area, so the amount of energy passing through the small squares, decreases as the squares of the distance from its source. So basically it's saying the closer it is to the object, the higher it's going to be. It's going to decrease the further and further it gets. That light spreads out a lot farther. Same thing with if you ever hold a flashlight up. The closer you are to the wall, the more condensed that light's going to be. Then the further away, the more spread out that light's going to be and allow you to see a larger area. So that's basically what it's saying. Okay, so now we're going to look at some pictures from Shadron and then from James Webb. So these are from the first ones are the pictures from the Shadron Observatory. That is X-ray radiation. And again, they're linked on the slide so you can follow along. So these are absolutely beautiful. This is our most powerful X-ray telescope that we have, our observatory. So we can see these beautiful images come through. So this one is gas. So the hues of pink and blue. So this is 11 million light years away from Earth. So 11 million years from here. Then we have this cluster here that shows a bunch of galaxies clustered together. So a lot of it is blue, and again, depending on what you're looking at for the objects. Then we have a supernova that was shown as well. So again, if we didn't have this X-ray, we really wouldn't see anything. But with this X-ray and adding colors behind it, we can see where the hotter parts are and where the cooler parts are. There's another one. Helix Nebula. Again, you can see the different parts of it. Cartwheel Galaxy. And then the last one here is one of a really popular one as well. And then if we go back, we have James Webb. James Webb is an infrared radiation. So this one has longer wavelengths for us to see. So this is the James Webb telescope's gallery. So you can see some of the nebulas it has taken pictures of. So you can see how detailed those are. like that one right there is crazy. This is the picture that is the screen, or like the cover of our class on Google Classroom. This is one of the very first images that James Webb took. They call it the cosmic cliff. So it's absolutely gorgeous to see the depths within it. It almost doesn't look real. But with this infrared, we're actually able to see deeper than we ever have before. There's a couple others, so some clusters, some deep field imaging. So this is similar to what Hubble is taking pictures of, but these brighter parts are parts that we've never been able to see. And the little dots or the swirls are galaxies, which have solar systems and things within it. So it's crazy to see the different things that are just out there. So I highly recommend taking a look at those when you get some time. Okay, let's talk about radiation in the Earth's atmosphere. So the figure shows that the band of electromagnetic spectrum and how well Earth's atmosphere transmits them. So the higher frequency waves from space do not make it to the surface and must therefore be observed from space. Some infrared and microwaves are absorbed by water, thus are best observed in high altitudes. Low frequency radio waves are blocked by Earth's ionosphere. So as you can see, a lot of the higher frequency waves are protected, or we are protected from, by the Earth's atmosphere. And again, not the entire way, but a lot of it, especially like gamma, X-ray, ultraviolet. Obviously, some of it's still going to hit the ground, but not all of it. And that's why we need satellites and things to be able to observe it. Visible light, obviously going to hit the ground for us to observe. Infrared goes to about where planes fly. Again, we can still have some satellites to help with that as well. Things like microwave, radio waves, and beyond that, those wavelengths will hit the Earth's surface. Again, they have a longer wavelength. There's less for them to be impeded on compared to the shorter wavelengths, like a gamma ray, which have such a high frequency that they bump into particles a lot more than a radio wave would. So we do have a lot of radio satellites on the ground, or satellite observatories, so that we are then able to see. As you can see, a lot of our visual light observation towers or observation areas or observatories are found in higher altitudes, just to try and give it the best chance of collecting instead of getting interfered by the atmosphere. Okay, so we have types of electromagnetic radiation. Again, we just talked about these. So the shortest are gamma rays by 0.01 nanometers. So that's 1 times 10 to the negative 11th meters. So it's a very crazy high frequency, which also means it has a ton of energy behind it. X-rays are 0.01 nanometers to 20 nanometers. It has a high frequency. It also has a high amount of energy. That's why doctors don't like you to have a ton of X-rays done over and over and over again in a short period of time. It's because that's a lot of energy that your body is taking in, and a lot of energy that your cells are dealing with that can mess up your genetic information. UV is 20 nanometers to 400 nanometers. So it's blocked a lot by the ozone layer, but not all of it is. And then it has a very high frequency and energy. Again, we know ultraviolet light is not good for you, can cause skin cancer. And so we have to be really careful with that. Then we get into our little bit longer ones. So we hit visible light, which is between 400 to 700 nanometers. So radiation we can process. So it's a low frequency and energy. We have infrared, which is 1,000 to 1 million nanometers. We feel this radiation is heat as a very low frequency and energy. So that's why the Army and things like that will use night vision goggles to be able to see infrared. Someone will appear to glow because we emit that radiation because we feel it as heat, but we are not going to actually physically see infrared. Microwaves, and again, same thing as what is in our own microwaves, is 106 to 109 nanometers. Very low frequency and energy. That's why when you are warming something in the microwave, oftentimes you have to stir it, especially if it's a soup, because the inside will be cold and the outside will be hot, is because those wavelengths aren't strong enough to go through that substance. So you have to mix it up to then disperse the heat to then warm it again. And then the last one are radio waves. They are less than 109 nanometers, very low frequency and energy. That's why when you're driving in your car and you go through a valley, a lot of times you'll lose radio signal, and that's because it can get easily blocked pretty easily through a valley, and so you can just lose it, and it'll eventually come back as you go. Okay, so that's all I got for today. You have an Odigio quiz number 4 that should be posted. It'll be due next Tuesday, 10/10 by 3:15 p.m. I would use this time now. Knock it out, get it done, then you don't have to worry about it later on. And again, I will not see you Friday to remind you. I will see you Thursday though. So get it done now, then you don't have to worry about it. Let me know if you have any questions, and have a great rest of your day.